Up to now, we've taken a brief look at the results from proton-antiproton colliders. But another branch of high-energy physics experimentation involves experiments done on electron-positron colliders. Here we see the process of an electron-positron collision as modeled by the ABC Preon Model. An electron, composed of an A antipreon and a B preon, collides with a positron, which is an A preon and an anti-B preon. We've seen earlier how the production of a free A-anti-A pair leads to what is known as the Z signature in proton-antiproton colliders. And here we can see that the same production will take place in electron-positron colliders. Recall that the Z signature will result when the mass of the collision is such that the B and anti-B particles annihilate, leaving a free A-anti-A pair. Once that happens, a B-anti-B pair and a neutrino pair can be produced from vacuum, leading to two leptons, which is the signature for the Z particle. But in addition to forming a lepton pair, it is also possible that a C anti-C pair can form from the vacuum as well, and that will lead to various quark-antiquark combinations. Hence, it can be noted that the ABC Preon model nicely dovetails with the Standard Model. All of the various lepton and quark production channels known to exist in the Standard Model can also be seen to occur through the ABC Preon model. Of course, this is the idea behind all Preon models. The idea is that a simpler precursor model underlying the quarks and leptons will produce the known results and lead to an understanding of the composition of what are now known as quarks and leptons. We have just been discussing the possibility that A-anti-A pairs can be easily seen to result from electron-positron colliders, and we have shown how that production is consistent with known experiments. But note that it should also be possible to produce B-anti-B pairs as well, through the annihilation of the A-anti-A portions of the electron and positron. In that case, massive leptons will be produced through A-anti-A and neutrino pair creation, and a quark-antiquark pair will also be produced through C-anti-C production. This leads to a prediction for new physics from the ABC Preon model. A signature similar to the Z particle signature should also exist at about 69.6 GeV, as well as what it presently exists at 91.2 GeV. Note that it may not be as strong a signal as the one at 91.2 GeV due to a much smaller cross-section, but the signal should exist. And now let's return to a look at proton-antiproton collisions. Earlier we saw how the ABC Preon model leads to an understanding of what are presently described as W events through the formation of an anti-A preon and a B preon. We also saw how the model led to an understanding of what are presently described as Z events through the formation of an A anti-A preon pair. But, as was the case with the electron-positron colliders, it should also be possible to form B anti-B preon pairs from proton-antiproton colliders as well. Hence, the same physics seen at the 91.2 GeV Z peak should also be seen at a 69.6 GeV peak in proton-antiproton colliders. Since there are only half as many B particles as there are A particles, and half again as many anti-B particles as there are anti-A particles in these collisions, this will lead to only a quarter of the amount of the production at the lower energy peak than there is at the higher energy peak. Additionally, the cross-section for the production may be smaller, as evidenced by the more tightly bound B particles in the down family of quarks. but the signal at 69.6 GeV should exist in proton-antiproton colliders at some level. In addition to the events described so far, the ABC Preon model predicts several new classes of physical results at proton-antiproton colliders. Collisions can knock off both A particles from the proton and both anti-A particles from the antiproton, and this would lead to the formation of what would be described in the Standard Model as Z-pair production. Similarly, if one of the A's is replaced by a B in the previous example, the collision would result in a W and a Z signature. Or, if a B bar and a B are produced along with an A and an A bar, the signal would be reported as a W pair. Note that these results are obtained by the dressing of the W and Z particles into quarks and leptons, as has been described above. C particles and neutrinos and other A and B particles can be formed out of the vacuum by pair creation, and they will combine with the A and B particles to form the familiar hadrons and leptons seen in proton-antiproton colliders. That, of course, is an advantage shared by all Preon models. By forming a deeper understanding that still leads to the quarks and leptons at a higher level, all of the known physics using quarks and leptons is also understood. The Preon model dovetails into the Standard Model, keeping the successes of the Standard Model, while at the same time predicting some new physics and also simplifying our understanding of the world. Here we see a slide that shows some additional possibilities at proton-antiproton colliders. It is possible to produce an A and a B and two anti-Bs with a total rest energy of 150 GeV, or two B-B bar pairs at a rest energy of 139.2 GeV. It is also possible to produce free C particles, although that would likely result in many A and B particles being freed as well, since the C particle is bound to two A's and a B in the proton. If the C and C bar annihilate, the energy liberated could form additional particle pairs along with the freed A and B particles. Hence, there is a very large amount of physics possible to discover at proton-antiproton colliders. Of course, the flexible Standard Model may well have found some of this already. And since the ABC Preon model dovetails so nicely with the Standard Model, the new physics may have already been explained by some exotic decay channels. There is one experimental result where it may at first seem that the ABC Preon model fails, and that involves the experimental evidence for the top quark. On this slide, we recall our earlier depiction of the up family of quarks as the binding of an A particle to a C particle. But note that there should be no binding at all if the A can be freed from its bound. As an approximate upper limit, it should not be possible to have a quark form at a mass above twice the mass of the A, since putting that much energy into the bond should be enough to free the A from the C particle. Twice the mass of the A is of course 91 GeV, and yet the top quark has been reported to exist with a mass of 172 GeV. But the important thing to note here is that the top quark is theorized to decay very quickly. The experimental evidence consists of a bottom quark and a W boson. It is clearly possible to create a bottom quark in conjunction with a W boson in the ABC Preon model. Here we see the case where a C particle and three B particles are produced in a proton-antiproton collision. This combination of particles has a total mass of 173.4 GeV. And of course there is some range of uncertainty both in the top quark measurement and the A, B, and C Preon masses calculated here. So this combination has a mass that might be identified as the top quark mass. If an A-bar pair forms out of vacuum, The A bar B combination can be recognized as leading to the various W signatures, and one of the C-B bindings can form a bottom quark. So this may be the underlying cause for the top quark signature as found in high-energy physics experiments. Note that the high-energy physics experiments use active filtering of the data to look for specific things. In this case, a known signature of a W and a bottom quark was searched for, and it is easy to see how such a signature can arise in the ABC Preon model. But note also that the ABC Preon model also predicts that numerous other signatures will occur as well. The signature associated with a free C, A, and pair of B quarks is one such example, although there are many others. I believe it is clear from this webinar how to relate such signatures to events in high-energy physics experiments, and I further believe that if the search is made for these events, that they will indeed be found.